discussed about the property of linear expansion. Yeah, Karan, I have sent the notes and the video also of the last time's lecture. So you will get an idea from that also. In any case, I'm doing a bit of revision of what we did in the last lecture. So thermal expansion was the property that we had started with. And we had seen that in this linear expansion is given by the simple formula that fractional change in length is equal to coefficient of linear expansion multiplied by temperature change. Or we can also express it in this way, that the length at two different temperatures can be related in this way, where length L is equal to L1 at temperature T equal to T1 and L2 at temperature T equal to T2. Okay. And alpha is the coefficient of linear expansion, which is the material property. So this, along with an application of it, was what we discussed in the last lecture. Now today let's start with a further important application of this. Variation of the time period of a simple pendulum due to temperature. So we know that for a simple pendulum that oscillates like this, the time period is given by the formula 2 pi under root L by G. So if this is the time period at temperature T naught, the length is L naught. Okay. Then accordingly, we can see that at a new temperature, T naught plus delta T, L will become L naught plus delta L. So the time period will become this. Okay. So we now compare this equation with this new equation. You can see that T divided by T naught is equal to square root of L divided by L naught, which is square root of 1 plus alpha delta T. Or to the power half. Okay. So just make a note of this concept up to this point here, then we'll discuss further. So from here now this next step is coming by equation 2 divided by equation 1. Okay, so hope you have finished writing down up to here. Now next thing, okay, just a minute. Yeah, this last step, so it's just the square root comes as a power. Square root of something is that same quantity to the power half. Okay. Now pay attention the next step. So if we have a quantity like this, 1 plus x to the power half, we can approximate it as 1 plus half x if x is very small compared to 1. So this process is called the binomial approximation method. Okay. So by applying that over here, now we can see that alpha delta t is very small compared to 1, because remember alpha's order of magnitude even for metals is 10 raised power minus 5 per degrees. So therefore 1 plus alpha into temperature change to the power half can be approximated as 1 plus 1 by 2 alpha delta t. So therefore t by t naught, which is square root of 1 plus alpha delta t, can be approximated as half of 1 plus half of alpha delta t, or t is equal to t naught 1 plus 1 by 2 into alpha delta t. So t minus t naught is t naught into half alpha delta t, or the fractional change in time period is this. Okay. So in other words, fractional change in time period is half of fractional change in length. That's why it is half of alpha delta t. So the simple way to remember this is from Error's propagation concept. If y is equal to k into x to the power n, then fractional or percentage change in y becomes n times fractional or percentage change in x. Okay, so like that, time period is proportional to square root of L. So that means time period is some constant into L to the power half. So fractional change in time period will be half of fractional change in length. So this is an easy way to remember this concept. That doesn't matter whether we write it as T naught or T. This is the general expression. Now that was specific. This is the general formula. Okay, I'll scroll up. Okay, so let's now look at an example problem based on this. So pendulum of a clock, okay, has its bob suspended by a thin metallic wire of coefficient of linear expansion so find the percentage change in its time period for a temperature rise of 50 degrees C. Okay. So second, if the clock is calibrated for accurate timekeeping at a temperature of 2 degrees C, then find the percentage error at 52 degrees C. Okay. Will the clock be gaining or losing time at 52 degrees C? And third, calculate the time in seconds lost or gained per day at 52 degrees. So let's just try out this question next. Okay, so we'll see actually the first two parts are the same answer. For delta T equal to 50 degrees C, the fractional change in length is 10 raised by minus 4, or we can say 0.01%, okay, increase in length. So therefore, so 0.005%, that's correct. Increase in time period. So this is the answer to both first and second part. So that will be the percentage error in timekeeping at 52 degrees C. Okay. So if the time period increases, that means it will lose time. Because the pendulum is taking longer to oscillate than it should in correct timekeeping. That means the clock is running slower. The pendulum is taking longer time. That means it's running slower. So the clock will be losing time. So what about the third part? Anybody got the answer? Still waiting for the answer of the third part. Now that you got the percentage error and you know that it is losing time, it's very easy to calculate. No, check your calculation, Yash. So then what? And first of all, will it? So it loses time at the rate of 0.005%. Therefore, in one day, it loses 0.005% of these many seconds. So that is, okay. So these many seconds it will lose it. Okay, so it loses 4.32 seconds per day. So in about a week, it will lose half a minute, significant amount of time. Okay, so hope this is clear, people. So this is the method of doing the calculation for variation of time period of pendulum clocks. Okay, just remember this basic concept. You don't need to memorize the formula. Time period is proportional to square root of L. Therefore, fractional change in time period is half of fractional change in length. So that is half of alpha delta t. So just this relation, if you keep in mind, rest you can do logically, like we did in this question. Okay. Now let's move on to the next part, which is surface expansion first and then volume expansion. Surface, or sometimes it is also called superficial expansion. They both mean one and the same thing. So suppose A is some surface area. Okay. So for example, A could be pi r square for a disk of radius r, or A could be 4 pi r square for a spherical surface of radius r. Okay. Or A could be L into B for a rectangular lamina, etc. Any such. Okay. Or A could be, for example, 6L square for the surface area of a cube of dimension L by L by L. Yes. So any such thing. Now, any surface area also expands, undergoes thermal expansion according to the formula that fractional change in area is directly proportional to temperature change. Okay. And the constant of proportionality beta is called the coefficient of surface expansion. It's very similar type of formula, okay, which is as a consequence of the formula we have seen earlier actually. So the important thing here is that for any given material, the value of beta is nothing but double the value of alpha. It is 2 times the value of alpha, and this is just a mathematical principle. There is no material property involved here. That whatever will be the coefficient of linear expansion, the surface area will expand according to a coefficient which is double of that. Okay. So we'll just understand the logic behind this statement also in a moment. But first, just note down this part. Okay, so now the logic behind this is very easy to understand. For example, if we consider a rectangle which is having this kind of dimensions at temperature of T naught. Okay, so this will tend to undergo an expansion at a new temperature. So it would have expanded to L by B. Okay, so L would have become L naught 1 plus alpha delta T. The breadth also would have become the same relation because L is a linear dimension. B is also a linear dimension. Okay. But the area has a dimension of L square. Length and width both have the dimension of capital L. Okay. So now if you compare this expression with this expression, you can see that A is equal to A naught 1 plus alpha delta T whole square. Okay. But alpha delta T is very small compared to 1. So therefore, 1 plus alpha delta T whole square is 1 plus 2 times alpha delta T. Again, binomial approximation. So by that logic, we can see that A is equal to A naught 1 plus 2 alpha delta t. Okay. So from this, we can see that the value of beta will become twice of alpha. Or another example you can see is, suppose we are talking about a disk which has radius r naught. So area equal to pi r naught square at t equal to t naught. So at t equal to t naught plus delta t, the radius becomes r naught 1 plus alpha delta t square. Sorry, 1 plus alpha delta t. So the new area becomes pi r square. Okay, so that is pi r naught square 1 plus. So from this you can see that beta is equal to twice of alpha. So it's really, in a sense, it is application of binomial approximation or concept of error propagation. So just make a note of this quickly. Yeah, Aditya, I'll scroll up. Okay, so let's now understand one important aspect about thermal expansion, and that is the behavior of a cavity or hole in a material due to temperature change. Okay. So imagine we have this kind of an object, like we've taken a metallic sheet and cut out a round hole. Okay. So this is a rectangular metal sheet with a round hole. Okay. So the sheet has dimensions L by B. Okay. So if alpha for the metal is equal to 8 into 10 raised power minus 6 per degree C. So when the temperature is increased by 40 degrees C, we want to find the percentage change in length, width, radius of the hole, and surface area of the metal sheet, and also the area of the round hole. Okay. So when you're answering this question, you have to also understand in perspective of whether the percentage change is a positive percentage change or a negative percentage change. That means, for example, if I'm talking about the area of the round hole or increasing the temperature, does the area increase or decrease? Yes, yes, that is correct. Yes, Bhaviskar. You're referring to the area of the hole? Yes, so your answer is correct. That will also behave in that way. Okay, so about any cavity or any hole in a material, what we have to understand is that the cavity or hole always increases in the same way like the material which has been removed. Okay, Vashish, so I'll come back to the calculation part, but the important thing to understand about the dimensions of the cavity is that a cavity or hole, okay, expands on temperature rise or contracts on temperature dropping exactly like the material that was removed to create the cavity. So for example, here, in order to create this round hole, suppose we have cut out this metallic disc. Okay. So this metallic disc has been cut out. So this has a radius R0 at temperature T0. Okay. So now what will happen is that at the new temperature, it's not only the outer dimension that will increase, okay, but the dimension of, sorry, this thing will also increase in the similar way. Yeah, just a second. Yeah, so at a new temperature, L will become L naught 1 plus alpha delta T. B will become B naught 1 plus alpha delta T. That radius of this will also expand. Okay. Just like this thing would have expanded. This would have expanded to R. When I increase the temperature, okay, T equal to T naught plus delta T. So this is what happens. So you can see that okay, and metal surface area, let's say, is A. So that is L into B minus pi R square, okay, into 2, because there are two sides of the metal. Now this area of the metal will also expand according to this, and the whole area or the cavity area, this pi R square, that will also expand according to beta delta T, where beta is 2 times alpha of the metal. Okay. So this is the important concept here. Just make a note of this first, then we'll complete the calculation. Why multiplied by 2? Because we are calculating the total metallic surface area. Na? So there are two surfaces, the front and the back. I mean, suppose you're sticking paper on the metal surface, na? It will have to be two sheets. So that way, if you see surface area, if you just casually say area of the plate, then it's fine. It is L into B. But what is the actual surface area of metal which is available to you? That is 2 times L into B minus the area of the cavity. Yeah, I'll scroll down. Okay. Just a minute. Couple of people have to write down some stuff. So okay. So now all you have to do is plug in these values over here. We're increasing the temperature by 40 degrees. Okay. So just use these values now, and from this calculate the percentage change in each of these quantities. Okay, so anybody got the answers for the percentage changes? So everything increases, okay, but these first three quantities, they are linear dimensions. So the percentage change will be the same for them. Delta L by L percentage will be equal to delta B by B percentage will be equal to delta R by R percentage, which will be alpha delta T converted into a percentage. So that is how much now. 0.032, isn't it? Yeah, so as a percentage change, it will be point. No, that is alpha, na beta. 8 into 10 raised power minus 6 is the value of alpha. Okay, so okay. So now these two quantities, their areas. For both D and E part. Okay. So the area of the surface area of metal as well as the holes area. Yes, that's correct. So Yeah, Joe will see what is happening. The coefficient of linear expansion, okay, that is given to us in the question. The coefficient of linear expansion of the metal that is given to us in the question as this value. And the temperature is rising by this much. Okay. So any linear dimension that will have a fractional change. Let's say delta, any linear dimension x will have a fractional change of alpha delta t. So here x could be the length, x could be the width, x could be the radius of the disk that we have cut out. All of these are linear dimensions. Understood? So when you're converting to a percentage, you multiply by 100. Got it now? Whereas any area dimension, any surface area, E, this could be area of the metal surface, this could be the area of the hole, whatever be the case. Okay. So metal surface is twice of LB minus pi r square. Area of the hole is just pi r square, but they are both area dimensions. Okay. So the fractional change for these dimensions will be equal to beta into delta t, where beta's value is twice of alpha. So that's why they will have double the percentage change. Have you understood now, Joel? So very simple concept like this we apply over here. Okay. Now let's move on to the next part, which you must have understood by now, is about volume expansion. So that's just a continuation of this. So volume expands with temperature according to this sort of a relation, where gamma is called the coefficient of volume expansion. Okay. And gamma is equal to 3 times alpha, just like beta was twice of alpha. So for example, if we have a solid cuboid, okay, of dimension, okay, some kind of height, some kind of length, and some kind of width. So the volume is L into B into H. So we know that delta L by L is equal to delta B by B is equal to delta H by H, because they're all linear dimensions. So they will change by a fractional change of this much. Now volume is equal to product of the three. Okay. So if the volume was equal to L naught into B naught into H naught at some temperature T naught, then the volume is L into B into H at T naught plus delta T. So that is L naught 1 plus alpha delta T. Similarly, for the width, and similarly for the height. Okay. So it's very similar. But this factor of 1 plus alpha delta T is multiplied thrice now, because volume is dimensionally equal to L cube, it's cube of length. So this volume in general should be equal to the original volume into 1 plus alpha delta T cube. But remember that alpha delta T is generally speaking very small compared to 1. So again, we can apply the binomial approximation method. And that's how this relation will reduce to this step. Okay. So we can see that V is equal to V naught, 1 plus 3 times alpha delta. Okay, so gamma is equal to 3m. Okay, yes, I'll scroll up. Okay, so this is the concept of volume expansion, right? And as discussed here, the main important thing to remember that the value of gamma for any material is 3 times alpha for that same material. An easier way to just remember this is that, if you have a solid sphere, okay, if its radius is r, then its surface area is 4 pi r square and its volume is 4 by 3 pi r cube. So from this relation, you can easily understand that delta A by A will be 2 times delta R by R. And from this relation, you can understand that delta V by V will be 3 times delta R by R. Okay. So if delta R by R is alpha delta T, because R is a linear parameter, it's a linear dimension. So delta A by A should be beta delta T. You can see that alpha is 2 times, beta is 2 times alpha. Very simple relation. And you can see that the fractional change in volume, so the coefficient of volume expansion should just become thrice. Okay. So this is all coming from that same concept.
Sir,
Binomial
how,
approximation.
sir, I did not understand that how 1 plus alpha delta the whole cube is 3 alpha delta t plus 1.
Sorry, come again. You did not understand?
Sir, that binomial one you told that approximation one.
Yeah, this step, now I've written it down for you. You just copy down this step, this concept.
Yes, sir,
This comes
that
from binomial theorem. 1 plus x to the power n is approximated as 1 plus nx when x is very small compared to 1. It's the same thing that we used earlier today. So, for example, square root of 1 plus x becomes approximated as 1 plus half x. Like that, 1 plus x whole square becomes approximated as 1 plus 2x. Like that, over here, we're just using the value of n as 3. So it's nothing different really. Okay.
yes, sir.
So this theorem in mathematics, this is called the binomial approximation theorem. So this is a direct application of that theory. Is it clear now?
Yes, sir.
No. Okay. So now the final consequence of this volume expansion, we'll see density of a material varies with temperature, whereas mass does not. Okay. So variation of density, which will denote with the symbol rho with temperature. We'll just use a simple relation that density equals to mass per unit volume. Okay. So density is mass upon volume. Therefore, if rho naught is equal to m by v naught at the temperature T equal to T naught, then at a new temperature T naught plus delta T, the volume, as you know, will become this. So density can be written as m by v naught 1 plus gamma delta T. So we compare this equation with this equation. You can see that we come up with the analysis that the density at the new temperature is the original density into 1 divided by 1 plus gamma delta. So once again, you might have guessed that we will be using binomial approximation. But for that, we will first bring this to the numerator by raising this power. And then next, we will once again use that fact that 1 plus x to the power minus 1 can be approximated as 1 minus x for x being very small compared to 1. So that concept here. So density decreases with increase in temperature. It's very simple. If the volume expands for the same amount of mass, then the density should be decreasing. So that's the concept here. Okay, so let's put together all this with a numerical example question. So in this example question, what's happening is that we have a glass container. Okay, finish writing that down first, then we'll come back to this question. Yeah, okay, done now. Oh. So next up, we have this example problem where we have a glass container. So suppose the coefficient of linear expansion of glass is given to us as this much, okay. And this glass container at room temperature, it has base area of 10 centimeters square, and it is filled with some liquid up to a height. So now that liquid has a gamma of 9 into 10 raised to minus 4 per degrees, and it is filled up to a height of these many centimeters at T naught is equal to 27 degrees. So now the temperature of the container plus liquid is raised to, let us say, 47 degrees. So first of all, find the percentage change in volume of liquid and density of the liquid. And secondly, the new height h of the liquid at the temperature of 47 degrees. So just try this out, people. So through this, we will clear the concepts that we've discussed in the last few minutes about surface expansion, volume expansion, variation of density with temperature. All these things we'll understand through this question. Assume that liquid does not overflow on increasing the temperature. Yes, that is correct. So you can see that for the liquid, delta V by V will be gamma delta T. Okay. So that is gamma of the liquid. So that is this value into temperature change. That is from 27 to 47. So into 20. So that is 1.8 into 10 raised power minus 2. So percentage change is 1.8% rise in volume. Okay. So accordingly, the density okay, is a 1.8% drop. Now for the second part, what you have to understand is that the area expands. Yes, Vashisht, that's correct. Very good. For the second part, what you have to understand is that the area of the container's base that expands. So A will be equal to A naught into 1 plus beta of glass into delta T plus the volume of liquid expands. So the new volume of liquid will be the original volume of liquid into 1 plus gamma of liquid into delta T. Now V naught was equal to A naught into H naught at T equal to T naught. And the new volume will be equal to the new area into new height at T equal to T naught plus delta T. So from this now you have to calculate how much the new height. Understood? So you have to take into account the fact that the base area is also increasing. It's not just that the volume of the container is, the volume of fluid is increasing. Yeah, Joel, just now we saw the formula, no? That density is mass divided by volume, no? So density is inversely proportional to volume. So the volume increases by a certain percentage, the density will decrease by that percentage. Delta rho by rho percentage is minus gamma delta T. Variation of density with temperature we saw is minus gamma delta T. It is just negative of the variation in volume with temperature. So this relationship holds true because density is inversely proportional to 1. Yes, exactly that one. Good. Okay, so let's understand this now. So from this relation, we can see that originally what was the volume of liquid that we had? It was the base area of the container, which was 10 centimeter square multiplied by 20. So it was 200 cubic centimeters. Okay. So the new volume of liquid that we'll have from here, 200 into 1 plus gamma of the liquid, which is 9 into 10 raised power minus 4 into the temperature change, which is 20. Okay. So this is the volume of the liquid in the container at this temperature. So it is 200 into 1 plus 1.8 into 10 raised power minus 2. This we've already seen, centimeter. Okay. Now what about the area? This area would have become the original area, which was 10 centimeters square, okay, into 1 plus. Now from here you can see that beta of glass will be 2 times alpha. So that will be 1.2 into 10 raised power minus 4. Okay, I'll just check the calculation with that. So 1.2 into 10 raised power minus 4 into the temperature change, which is of 20 in centimeters square. So that is 10 into this much. Okay. So now we'll use this formula. So the new height will be the new volume divided by the new area. So the new volume is 200 into 1 plus 1.8 into 10 raised power minus 2 centimeter cube divided by the new base area, which is 10 into 1 plus 2.4 into 10 raised power minus 3 in centimeter square. So you can see that this new height will be 20. Now we can bring this in the numerator. So we can bring this factor of 1 plus 2.4 into 10 raised by minus 3 to the numerator by putting the power minus 1, and the unit will become centimeters. Okay. And next step again we'll use binomial approximation. So we'll bring the power inside. So this will become 1 minus 2.4 into 10 raised by minus 3. Okay. And next we'll open this bracket. It becomes 1 minus 2.4 into 10 raised by minus 3 plus 1.8 into 10 raised by minus 2. Okay, minus 2.4 into 1.8 into 10 raised by minus 5. Now this term, we can neglect this term because its order of magnitude is 10 raised by minus 5. So it's very small. So we can say that this is and these two terms, if we put them together, become like this: 1.8 minus 0.24 into 10 raised by minus 3. So 10 raised by minus 2. So the new height will become something like this. Okay, so people hope the method of calculation is clear. Okay, so this chapter is very easy, but just you have to keep in mind that while doing calculations, you can always make use of binomial approximation method, which we discussed in a number of things today. Okay. Yeah, because see, the thing is, if you don't neglect that 10 raised power minus 5 wala factor, is going to figure out in the fifth place of decimal. But you are going to report the answer only approximated up to second place of decimal. Na? So anyway, it is negligible. Understanding the point? Na? That's why we are neglecting it, because these other two terms were up to 10 raised power minus 2. Na? That's the idea, basically. That's how we make the judgment of whether we are neglecting a term or not. Okay, so with that, we complete this section of thermal expansion. Now, I will just give you a brief introduction into the next section, which is called calorimetry. So, calorimetry is to do with the relation between heat and temperature for a given body. Heat supplied or absorbed versus temperature change. Okay, or state change, whichever is applicable. Yes, exactly. While doing the calculation, you have to be able to judge which term you can neglect, okay, because its value is small enough. Okay, so here what we understand is that if we are supplying heat to a certain material, which is, let's say, initially in solid state. So Q is on the x-axis, it is heat supplied, and temperature is on the y-axis, which is temperature. So Q is heat supplied, okay, to a material, and T is the material temperature. Then the graphical relationship that we get between these is like this. Let's say initially we start from solid state. So the temperature will rise with heat supplied, but till it reaches a certain point called the melting point, then the temperature remains stable while melting takes place. Then again the temperature rises with heat supplied till it reaches something called boiling point, where the liquid vaporizes. And when vaporization is complete, again the vapor temperature increases with heat supplied. So this is solid. Okay, then at a certain temperature called the melting point, the state change of melting takes place. And once melting is over, the material is in liquid state. And again its temperature starts to rise till it reaches a specific temperature called boiling point. And the moment we reach boiling point, heat supplied results in boiling or vaporization. And only when the vaporization is complete and the complete material is now in vapor state, further heat supply results in temperature variation. So at any temperature for a solid below its melting point, okay, the heat supplied is directly proportional to temperature change. So temperature increases uniformly with Q, and that relationship between the two depends on two things: the mass of the material and a property of the material called specific heat capacity. So from here you can see specific heat capacity is Q upon M delta T. So it is heat supplied per kilogram or per unit mass per degree change in temperature. Okay. So specific heat capacity for a material, okay, the specific heat capacity is the heat needed per unit mass per degree change in temperature. So that's why specific heat capacity is measured in joules per kilogram Kelvin. Okay. Or it can also be expressed in calories per gram degree C. For example, if specific heat capacity of ice is 0.6 calories per gram degree C and 20 grams of ice at minus 10 degrees C are heated to minus 5 degrees C. So you want to find the amount of heat supplied. So Q is just going to be ms delta T. So 20 grams into 0.6 calories per gram degree C into a temperature change of 5, because you're going from minus 10 to minus 5. So it will be 60 calories. So 60 calories of heat will have to be supplied for this change to increase the temperature of that many grams of ice from that initial temperature to this final temperature. Okay? So this is the definition of specific heat capacity. Okay, so this next section is also going to be very easy, and based on this definition and another simple definition called latent heat, which we'll discuss. Okay, so we'll conclude today's session here, people. And next lecture, we'll discuss more about latent heat and numericals related to specific heat capacity and latent heat. Okay. So in the meantime, please do questions from H.C. Verma's chapter of heat and temperature, which are based on thermal expansion. And also you can do from the module. We'll discuss 2 questions also in the next lecture. But this is a very easy section of the syllabus. So just refer to my notes before doing the question. You should be able to do. Yes, I will send it. Okay. So that's it for today's session, people. Wish you all the best.